Hello everybody. In this lesson, we'll explore NASA's CMAP's Turbofan engine degradation dataset. Our primary goal will be to predict the remaining useful life to turbofan engines using various machine learning techniques. We will start by performing exploratory data analysis on the first dataset, and it is FD001 to understand its structure and identify key patterns and trends. And this will involve loading the data, inspecting it for any anomalies, and visualizing different features to gain insights into the engine's performance over time. After completing the EDA, we will develop a baseline linear regression model to predict their RLU, remaining useful life of the engines. And we will pre-process the data, select relevant features, and train the model. Then we will evaluate the model's performance using metrics like root mean squared error and R-squared score. And this foundation model will serve as a benchmark for more advanced techniques that we'll explore in subsequent lessons. And let's begin with the code, and let's examine that. Here we import necessary libraries for data manipulation, visualization, and machine learning. And here, let's look at this. What happens here? We define the column names for the dataset, which include unit number, time cycles, operational settings, and sensor readings. And here, we load the training and test datasets along with the remaining useful life values for the test set using the predefined column names and train head. The first 5 rows on the training data are displayed, showing the structure of the dataset with 26 columns, and columns are unit number, time cycles, and setting 1, setting 2, setting 3, and here setting 21. What we can say, let's look at these lines here. We use describe to get summary statistic for unit number and time cycles. And let's look at this. This confirms that the dataset contains data for 100 engines and provides insights into the distribution of time cycles. And what we can say here, summary statistics for units and time cycles are displayed, and the count for what column is 20,631, indicating the total number of rows, and the unit number ranges from 1 to 100. And let's look what we can see another, and confirming there are 100 engines, and the time cycles column shows a mean of 108.8 cycles with a minimum of 1 cycle and a maximum of 360 cycles. And let's look at another parts, and let's look at these parts. This code groups the dataset by engine unit number and calculates the maximum time cycle for each engine. And here the describe function then provides summary statistics for these maximum cycles, and this helps us understand how long on average the engines operate before failing. The variability in these cycles is captured by standard deviation and percentiles. And let's look at this output, and what we can say here. The summary statistics for the maximum time cycles of each engine are displayed, and there are 100 engines with a mean maximum time cycle of 206.31 cycles. The minimum maximum time cycle is 128 cycles, and the maximum is 362 cycles. And the standard deviation is 46.34 cycles, indicating variability in the cycles at which engines fails. And what we can say, the 25th percentile is here, 177 cycles, and the median, I mean 50th percentile is here, is 199 cycles, and here 75th percentile is 229.25 cycles. And let's look at our another parts and talk about this. Here, train setting names and describe. This code provides summary statistics for the operational settings in the dataset, and a very small standard deviation for setting 1 and setting 2 indicate that these settings do not vary significantly. Setting 3 is constant, suggesting it doesn't change at all these datasets. And what we can say here, summary statistics for the 3 operation settings are displayed, and the count for each setting is 20,631, indicating the number of rows. And the mean values for setting 1 and setting 2 are approximately 0 with very small standard deviation indicating minimal fluctuation. And setting 3 has a constant value of 100 across all rows. And let's switch and let's look at our another part and what happens here. This code provides summary statistics for the sensor readings. By transposing the result, the statistics are displayed in a more readable format, and the standard deviation helps identify sensors with no variability, which can be excluded from further analysis. And what we can say here is the summary statistics for the 21 sensor readings are displayed, and the count for each sensor is again 20,631, and sensors like S1, S10, and S18 and 19 show no variation. I mean standard deviation is effectively 0. And here other sensors such as S9 here and S14 show higher standard deviations, indicating more variability in their readings. And let's switch. We have a function here, and we will talk about this. And what happens here? Our function names add remaining useful life. This function adds a new column RUL, I mean remaining useful life, to the data frame, which represents the remaining useful life of each engine cycle. And the data frame is grouped by the unit number to calculate the maximum cycle each engine reaches before failure. And the maximum cycle information is merged back into the original data frame. This adds a max cycle column to each row, which holds the maximum cycle value for the corresponding unit number. And the remaining useful life is calculated for each row by subtracting the current cycle time from the maximum cycle. And we will drop the values here. The temporary max underscore cycle column is dropped from the data frame as it's no longer needed. And applying part, the function at remaining useful life is applied to the training data frame, and the first few rows are displayed to verify the new columns. And let's look at our output. The first 5 rows of the modified training data are displayed, and each row now includes a new column, remaining useful life, showing the calculated remaining useful life for each engine cycle. And for example, unit number 1 time cycles 1, and the remaining useful life is 191. And let's switch and talk about this code block and what happens here. And what we can say here, the data frame is grouped by unit number, and the maximum remaining useful life for each engine is computed. And here plotting parts. The histogram of the maximum remaining useful life values is plotted with 15 pins and a figure size of like that, and you can change and you can look like the bigger or more less. And the X label and Y label are set to remaining useful life and frequency respectively, and the plot shows the frequency distribution of maximum remaining useful life values, helping to visualize how long engines tend to last before failure. And let's look at our visual and talk about this. Okay, it's okay now. A histogram is plotted showing the distribution of the maximum remaining useful life for each engine unit, and the histogram confirms that most engines fail around here 200 cycles, with a few engines lasting beyond um, 300 cycles, and the distribution is right skewed. And let's switch, and we have another function here. And what happens here? The function plot sensor takes a sensor name as an argument and plots its reading against the remaining useful life for each engine. And here a new figure is created with a specified size of like 13 and 5, and you can change. The function loops through each unique engine in the training data, and what we can say, for engines whose unit number is divisible by 10, it's plotted sensor readings against remaining useful life, and the x-axis is set to range from 250 to 0, reversing the axis to show remaining useful life decreasing towards failure, and x-sticks here are set to display at intervals of 25, and y-axis is labeled with the sensor name, and the x-axis is labeled remaining useful life, and the plot is displayed using plot show, and the plot sensor function is called for each sensor in sensor names, generating a series of plots. And we will see the our sensors and the plots, and it is a little more. And let's switch, and we'll talk about them. Let's switch, and okay, let's stop here. The plots generated show the sensor readings against the remaining useful life for selected engines, and the x-axis is reversed so that remaining useful life decreases from left to right. And due to the large number of sensors, only a few representative plots are shown, and sensors such as like that. And what we can say here, and let's talk about this. And sensors 1, 10, and 18, 19, 5, and 16 show no useful information, and while others, I mean 2, 6, 7, 12, 20, 21, 9, and 14 exhibit various trends and patterns that can be used for modeling. And this sets the stage for developing a baseline linear regression model. And let's switch and talk about our evaluation part here. What happens here? This function evaluates the performance of the model by calculating the mean squared error and root mean squared error and R squared score, and y true RUL values, and y hat here true remaining useful life values, and label it indicates whether the evaluation is for the training or test set. And let's look at the MEC, mean squared error between the true and predicted values, and RMSE. What is this? square root of MEC indicating the average prediction error in the same units as the target variable, and variance here R squared score representing the proportion of the variance in the dependent variable that is predictable from the independent variables, and we will print the results in the last lines. And drop sensors, what happens here, and let's talk about this part. Here columns unit number, time cycles, operation settings, and sensors identified as not useful are dropped from the training and test datasets, and X-train features for the training set excluding the dropped columns, and Y-train target variable for the training set extracted from X-train, and test data, I mean here X test features for the test set proceed to keep only the last cycle for each engine and exclude the dropped columns. And let's switch and let's look at the linear model part. Here LM linear regression, it initializes the linear regression model, and LM fits the model to the training data. And Y head train, what happens here, it predictions for the training sets and it evaluates the model's performance on the training set. And Y head test, here predictions for the test set and evaluate, finally here it evaluates the model's performance on the test sets. And let's look at our outputs. What we can say, the RMSE values indicates the average error in predicting in the remaining useful life for the training and test sets, while the R-squared scores indicate the proportion of variance explained by the model, and the lower RMSE on the test set compared to the training set is counterintuitive and might suggest overfitting or issues with the remaining useful life assumption used. And let's stop here. I think it is enough for our linear regression model and lesson, and see you in the next lesson.